So this example is number 20.11 from chapter 20 of the text, and I'm actually going to go through this two different ways. Once through using Excel, and the other just doing it manually. So I'm going to start with a manual, and I have a little bit of help with Excel in the background just so that we can speed up the number of computations. But the question here is whether or not black eye grease actually reduces glare or not. And so a study was done. 16 student subjects took a test of sensitivity to contrast after 3 hours facing into bright sun. They did it once with the grease and once without the grease. So greater sensitivity to contrast improves vision and glare, reduces sensitivity to contrast. This is what we call a matched pair design. So this is an example of a matched pairs design where you have one study that's being done, and there's one scenario represents one set of numbers. The second scenario represents the second set of numbers, and in this case, it's with the grease, and the second part of the pair is without the grease. And so what they've done here is they've taken the differences in the sensitivity. Each of these numbers represents a football player or an athlete that was measured, part of the study. So there should be 16 of these. So 16 athletes were used, and this is for each of these numbers is the difference between the two different environments, one with and one without the grease. So they want to know whether the eye grease increases sensitivity to contrast on average. So, the first thing we want to do is we want to look at what our hypotheses are. What's the question that we're trying to ask? Well, we know that our null hypothesis in this case is going to be nothing happens. There's no change. And we'll call this mu equals 0, and then a change would be our alternative hypothesis, so a positive change, and that would mean that our mu would be something other than 0, so it would be greater than or equal to 0 in this case. Actually, it would probably just be greater than 0. So, so these are our statements, the hypothesis statement. We also know that n is 16, and we can calculate our standard deviation and our mean, so our x bar and our s for the sample. So we have all of the data right here, and we can calculate those. So we will do that momentarily. And we're going to set our significance level, and we're going to set that to, we'll just say 0.05 or 5%. So that's our level of significance to gauge whether or not a change is actually significant or not, and whether the black grease actually helps. So here's all our data. So we've got this all laid out. The only thing we need to do is calculate x bar and s, and I've gone ahead and actually done that in Excel, and I won't show you that yet, but there is another video that will have the Excel work done in it and show you exactly how to get those numbers. But if you even did this by hand, you should get an average here of 0.10125, and then you should get a standard deviation of 0.226329. So those are our numbers, and we can actually just round those to the nearest tenth even. So we can say 0. Or maybe 100th, 0.101, and we can round this to 0.23 if you want. The more decimal places you go out, the more accurate your result is going to be. So now we have all of our data laid out here. The next thing we need to do is actually figure out what our critical value is. And from that we can derive our p-value, which is ultimately what we want to get, because our p-value is how we're going to compare against the level of significance. So to do the to do these calculations, we're going to need to know that the critical t value here is going to be equal to, and we'll just actually call this the t statistic. So the t statistic here is equal to x bar minus our mu sub, we'll call it mu sub 0, or our null hypothesis mean, over our calculated s from our sample divided by the square root of the total number of samples taken. The other thing we want to note here is our degrees of freedom. So in this case, our degrees of freedom, sorry about that, our degrees of freedom are going to be 1 minus n, which is going to be 15. So I'm going to do the math here. I'm going to plug some of the numbers in. So our t statistic here is equal to x bar, which we've computed to be 0.101, minus, and in this case it's 0, minus 0 over s, which is 0.23, divided by the square root of 16. And if you do the math on this, you should get, and I'm looking here, you should get 1.789427 if you went out so many decimal places, something around there, which you can probably round to 1.79 as your t statistic. And so now you want to go to the table, and I'll bring the table up right here, and you want to look for that 1.79. And now we have a degree of freedom of 15, so now we know to go to the this line here, number 15, in our degrees of freedom, and now we want to look for that 1.79 or whatever's closest to the 1.79. So in this case, I'm going over until I see some 1.7 even, and here's 1.753, and it's between these two numbers here, 1.753 and 2.131. So I know that my p-value is going to fall somewhere in between there. So if I follow this down, and remember, we're trying to determine whether or not there's a positive change. So if I look at the graph, what we're trying to figure out is whether or not the t, we're looking over in this side right here. We want to see if there's something positive, if it's actually greater than what the null hypothesis is stating. So if I go down, this is a one-sided, because it's only one tail, we're not looking at both tails, it's a one-sided p. I can follow these down to the one-sided p row, which is right here, and I see that it's somewhere between 0.05 and 0.025. We know that our significance value was 1.05, and so this is saying that somewhere between 2% and 5%. So we know it's less than our level of significance, so therefore we can reject the null hypothesis. And we have sufficient evidence to note that the alternative hypothesis may actually, in fact, be true.